Now, coming to you live from the crawl space underneath McLean Hall. Foundations of Math and Pre-Calculus 10. Dance. 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 Today, Chapter 2, Trigonometry, Section 2.1, the Tangent Ratio. Alright guys, trigonometry, this is your first time having a formal study of it, but you know, it's really just an extension of the concepts of triangle similarity, which you studied last year in Math 9. Remember that if two triangles are similar, then the ratios of their corresponding side lengths must be equal. Take the two right triangles shown here. They're both 30, 60, 90 triangles, and since their corresponding angles are equal, then the two triangles are similar, meaning that the following proportions will be equal. If I look at the short side on triangle DEF, 2.5 from the 60 degree to the 90 degree, and I put that over the corresponding side length on the other triangle, 5.5, this will also be equal to the medium side length from the 30 degree angle to the right angle over its corresponding side on the other triangle. And likewise, I could do 5 the hypotenuse over 11 the hypotenuse on the other triangle. So I can do comparisons from one triangle to the other. I could also do comparisons within one triangle. For instance, 2.5 over 4.4 is going to be equal to the same proportion of the short side to the long side on the big triangle. That would be 5.5 over 9.5. Those proportions would be the same. Or I could look at 5.5 over 11, the short side over the hypotenuse, would have to be equal to 2.5 over 5, the short side over the hypotenuse. And I could do the third one as well. So next we want to go a step further with this and start looking at how the side lengths here correspond with respect to the angles of the right triangle. Consider the right triangle ABC shown here. There's a few naming conventions first to talk about. The corners of the triangle, or the vertices, the angles, are always referred to with uppercase letters, while the side lengths are given in lowercase letters. We name the sides based on which angle is opposite to the side. So side little a is opposite from angle A. And likewise sides B and C are opposite from their angles. Another thing that we commonly do is refer to unknown angles with a special variable called theta. You know how we usually use x in algebra? Well, theta is what we usually use when talking about an unknown angle. Now, since this is a right triangle, we can work with the Pythagorean Theorem, a squared plus b squared equals c squared, and we can see here that little c is the hypotenuse. The two remaining sides are called the legs of the triangle. And if we're looking with respect to angle A, we can obviously say that side little a is opposite from it, while side B is adjacent to angle A. Of course, the hypotenuse is also adjacent, but we aren't referring to the hypotenuse, only to the legs. Now, earlier we said that the proportions of the sides of a 30, 60, 90 triangle are always the same. Well, then we can also say that the length of the opposite leg divided by the adjacent leg is always the same ratio. And this concept is the foundation of modern trigonometry. And we have a name for this ratio called the tangent ratio. Don't worry about the word tangent. It has origins in circle geometry that aren't really important right now. What's important is that you know that the tangent ratio with respect to one of the acute angles of a right triangle is always the opposite leg divided by the adjacent leg. In other words, tan theta is equal to opposite over adjacent. This ratio is usually expressed as a fraction or as a decimal number given to 3 or 4 places. In this case, tangent of angle A is little a over little b. Let's look at an example here. Take triangle DOG here and find the tangent ratios for the non-right angles. The tangent of angle D is the opposite over the adjacent, which is 11 over 4, which reduces to 2.75. The tangent for angle G is also the opposite over the adjacent, but in this case they're reversed. Opposite from angle G is 4, adjacent is 11, which gives you 0.36 repeating. I prefer the fractions in written form because I don't have to worry about rounding off my decimals. Now, since every angle measure has a unique set of side ratios, this means that the tangent ratio of 2.75 must be unique to one specific angle. If only someone had bothered to go to the trouble of finding each of those ratios first, we would be able to say, aha, a tangent ratio of 2.75, well, then I know the measure of angle D. Well, someone has bothered to go to the trouble. In fact, as far back as the 1st and 2nd centuries of the Common Era, we have Hipparchus and Ptolemy creating tables with lists of trigonometric ratios for just this purpose. And here's an example of a trig table and how you would use it. If we want to find which angle has a tangent ratio of 2.75, we look down the tangent columns until we find 2.75 or something very close to it. And then we just read over to see which angle does that ratio come from. We can do the same thing for 0.36 repeating. And notice that we get angles of 70 and 20 degrees respectively, which makes sense for our right triangle before, so that the total of the angles comes out to be 180 degrees. Since it isn't very convenient to carry a table like this everywhere you go, some brilliant person decided we should just put this into a calculator. Now, if you want to know the tangent of 30 degrees, you just type tan 30. Let's try another example now, using tangent to find a missing side length. The fictional character, Mr. Clausen, stands exactly 15 meters away from a flagpole. He determines that the angle of elevation to the top of the flagpole is 40 degrees. So how tall is the flagpole to the nearest meter? In a problem like this, the best thing to do is start off with your diagram. So draw your flagpole, draw the ground, draw your character 15 meters away exactly. And I want to think about angle of elevation. What does that mean? Well, if you consider looking straight ahead to be 0 degrees, then how many degrees do you have to turn your head up to look at the object in question? In this case, that is 40 degrees of elevation. You could also talk about angle of depression as how much would you have to look down at something. For instance, if you were on the flagpole, how far would you have to look down to see that spot on the ground? Since we know the distance to the flagpole, and we know the angle here, that means that in terms of the tangent ratio, 40 degrees, we have the adjacent side, but we don't have its opposite side. Let's call that opposite side h for height. So writing tan 40 equals h over 15 means that we can solve for h by multiplying both sides of this equation by 15, giving us 15 times tan 40 equals h. What's tan 40? Well, we could look it up in the tables, or just get our calculator to tell us. Tangent of 40 multiplied by 15, and there's the answer to what h is. Round that off to the nearest meter, and I think we're looking at approximately 13 meters of height. Oh, thanks, guys. Now let's use tangent to find a missing angle here. If you consider from angle T, we have the opposite and adjacent sides. Since tangent is opposite over adjacent, we can say that the tangent of angle T is 2 over 7, which on my calculator is approximately 0.2857. I could look that up in the table, but the best, again, is to use my calculator. Now, when we want to find the angle, we want to undo tangent. We want to find the inverse of the tangent. And so what we write is this notation here, tan negative 1 of 2 over 7. If you notice the tan button on your calculator, it says that same notation. So to access this, you press the second or the shift key on your calculator and have it give you the inverse tangent of 2 over 7. This means the angle is approximately 15.9 degrees, or to the nearest degree, why don't we say that angle T is approximately 16 degrees. And if you go back into the tables, you'll see that that's the number there. And now it's time for everybody's favorite part of the show.
Two for you.
Find the missing side lengths for triangle ABC and find the missing angles in triangle DEF. You can use some trigonometry for this, the tangent ratio, but you can also use other properties of triangles that you know. Pythag, what the angles have to add up to, etc. Have fun!